Hello viewers, in today's class we are going to discuss one very important and interesting problem from application of derivatives in which the concept of increasing and decreasing functions shall be used, right? So here we have to solve this problem which says that let p of x be a polynomial function, and we are given the condition that p of 1 is equal to 0 and p prime of x is greater than or equal to p of x for x greater than 1, right? And we have to show that the polynomial function p of x is greater than 0 for x greater than 1, right? So here we are given a polynomial function p of x, and the conditions are that when x is equal to 1, p of 1 is equal to 0, and the derivative of px is greater than or equal to the function p of x for x greater than 1, right? So utilizing these conditions, we have to show that the polynomial function is greater than 0 for x greater than 1, right? So let us start with this condition, right? So p of x is a polynomial function, right? And the derivative of the polynomial function for x greater than 1 is greater than or equal to the function p of x itself, right? So now we'll start from this condition, right? Now here what we will do, we'll take this p of x to the left hand side, right? So we have p prime of x minus p of x is greater than or equal to 0, right? And here p prime of x is equal to d by dx of p of x, right? Okay, now here what we will do, we'll multiply both sides by e raised to minus x, right? So here the important thing is that in inequality number 1, we'll multiply both sides by this factor, that is e raised to minus x, right? And we know that e raised to minus x is equal to 1 over e raised to x, and e raised to x is greater than 0 for all x belonging to the set of real numbers, right? So let us multiply both sides of inequality 1 by this factor e raised to minus x. So we'll get e raised to minus x. Here we have p prime of x minus p of x, and that is greater than or equal to 0, because here if we multiply 0 by e raised to minus x, we'll get 0, right? So now we can multiply these two terms by e raised to minus x. So we have e raised to minus x, then p prime of x, and here we have e raised to minus x and p of x, that is greater than or equal to 0, right? Now let us focus on this inequality number 2, right? So here we observe an important result, right? See, if we take e raised to x as a function u, right, where u is some function of x which is e raised to minus x, and let us take v as the function p of x, right? So v dash or v prime is obviously equal to p prime of x, right? So the derivative of v with respect to x, which is v prime, is equal to p prime of x. And similarly here, if we differentiate u with respect to x, we'll get u prime that is u prime is equal to minus e raised to minus x, right? So the derivative of e raised to minus x is minus e raised to minus x. So here see, we can write this expression as e raised to minus x p prime of x, then we can write minus e raised to minus x and p of x, that is greater than or equal to 0, right? Now e raised to minus x, we can now write here u, and p prime of x can be replaced by v prime, then minus e raised to minus x can be written as u prime, and p of x, that is v, right? And that is greater than or equal to 0, right? Now if we observe this term u times v prime plus u prime times v is nothing but the derivative of the product of u and v with respect to x, right? Now if we apply the product rule for this function, which is the product of u and v, then we take the first function, then derivative of second, then second function, and derivative of the first function, right? So now this term is now equal to d by dx of the product of u and v, that is greater than or equal to 0, right? So here we can now write this inequality as d by dx. U is e raised to minus x and v is p of x, right? And that is greater than or equal to 0, right? So now we have this important inequality. So now let us replace the product of e raised to minus x and p of x by some function, say f of x, right? So f of x can be written as the product of u and v, and u is e raised to minus x and p of x is v. So here we have p of x, right? So now this inequality number 3, it reads like this, that is d by dx of f of x is greater than or equal to 0, right? And this is a very important step, right? Now this step says that the derivative of f of x with respect to x, which is f prime of x, is greater than or equal to 0, right? And this is the condition for the function f of x to be increasing function, right? Because we know that a function is said to be increasing if its derivative is positive, right? And here f prime of x, which is the derivative of f of x with respect to x, is greater than or equal to 0, right? So this inequality suggests that this function f of x is an increasing function, right? So we have arrived at this important result, right? So we have proved that f of x is an increasing function, right? Now let us consider 2 points, right? Let us take x1 is equal to x and x2 is equal to 1, right? Because here we have to show that the polynomial function p of x is greater than 0 for x greater than 1, right? So let us take x as x1 and 1 as x2, right? So we are considering 2 points, right? And we know that from the definition of increasing function, if x1 is greater than x2, that is x is greater than 1, right? So we are given x is greater than 1. So when x1 is greater than x2, then f of x1 must be greater than f of x2, right? So this is another definition of increasing function, right? So now f of x1 is simply f of x, and f of x2 is f of 1, right? So now let us calculate f of 1 from this relation, that is f of x is the product of e raised to minus x and p of x, right? So f of 1 is equal to e raised to minus 1 by taking x is equal to 1 in this relation. So here we have p of 1, right? So we have 1 over e times p of 1, and we have 1 over e, and p of 1 is given to be equal to 0, right? So we are given that p of 1 is equal to 0. So here we have 0 and this is equal to 0, right? So f of 1 is equal to 0, right? So now we can write f of x is greater than f of 1 and f of 1 is equal to 0, right? Now f of x is e raised to minus x times p of x greater than 0, right? So we can now write this inequality as p of x divided by e raised to x is greater than 0, and we know that e raised to x is always greater than 0 for all x belonging to the set of real numbers, right? So simply here we have p of x that is greater than 0 for x greater than 1, right? And which is the desired result, right? So viewers, this is how we can solve this problem.